Hello everyone, this is Key. I'm currently a researcher at Visa Research. Today I'll be presenting our work, Blend, Precise, Semantic Programming Embeddings. This is a joint work with my PhD advisor, Jendong, who is now a professor at ETH. Let's start with the problem definition. What we are trying to solve in this work is to learn semantic embeddings of source code, which are continuous vector representations of programs, and a program denoting similar semantics should be mapped to vectors that are close to each other, where program denoting different semantics should be mapped to vectors that are far away from each other. This problem has been very well motivated, as we see many interesting works that have been published in this field recently. To give a couple of examples, MSR Cambridge folks defined a new class of bugs called variable misuse, for which GGNN, one kind of graph model, has shown a lot of potential. In this case, the class variable that is highlighted is misused. Instead, variable first should have been used. Later, Professor Mayo Naik's group proposed a model to generate loop invariants. Given the program on the left, it is pretty impressive that their model is able to synthesize a loop invariant of this kind. Also, Professor Iran Yahav's group has published a paper in Tuple last year on method name prediction, a task that is almost impossible for classical logic-based symbolic methods. The name of this function is reverse array, which is correctly predicted by their model. Despite the early success, there is a fundamental weakness of the prior static models. That is, unlike natural language, programs have a rigid and a well-defined semantics that might not be fully comprehended by finding patterns from a largely syntactic program representation, because subtle syntactic changes can result in drastically different semantics. On the other hand, vastly different syntax can also denote programs of equivalent semantics. Let me give you an example using a program that many people are taught to write when they first learn programming. Basically, it's about printing a chessboard with letter X and O, which represents the black and white square respectively. The correct program should produce this printing on the slide. Many students first come up with this program, not the most elegant solution, but does the job. In contrast, the program on the right is much more compact, at the same time quite different in syntax, even in their control flow graphs. But when you take a closer look, you will find two programs are semantically equivalent. Here is another way to solve this programming problem. You register what was printed last time and prints a different character next time. However, here lies an error. When it prints the last character in each line, it toggles the Boolean flag cursor, which it shouldn't have. As a result, you will wind up printing the same characters for each row. The printing looks like the one on the right. Rows within the red bounding boxes are handled incorrectly. Now to fix this error, one just needs to remove the toggle. An even simpler fix, while not necessarily best coding practice, but serves our illustration purpose, is to remove exclamation mark. In other words, a difference of one token leads to non-trivial semantic changes. So I think the challenge should be very clear by now, which is when a model only tries to discover patterns from source code, can it reason beyond the surface level syntax and capture the essence of the semantics? According to our study, it seems static models still have much room to improve. To address this problem, we proposed a solution 2 years ago. That is, instead of learning from the program syntax, models should learn from the program executions, which automatically canonicalize the syntactic variations or discern the semantic differences, even when their syntax is similar. In particular, we proposed 3 models, all learning from dynamic runs of a program. If you recall the example program, which troubled the static models, any one of these models would have little problem in dealing with them. If you're interested to know more, please refer to our paper published at ICR 18. Obviously, a pure dynamic approach is also flawed. First, a model that is built upon dynamic techniques will inevitably suffer from the inherent limitation of dynamic analysis. That is, the generalizability of a model can be severely affected if it is trained on executions that do not sufficiently cover a program. Second, even for a covered program path, dynamic models need many execution instances to generalize from, resulting in a lengthy, inefficient training process. So a natural next step is to combine both static and dynamic program features in a way that magnifies the benefits and alleviates the weaknesses of both approaches. We ground up new method as a dynamic approach for the sake of the precision, and we incorporate symbolic features to reduce the heavy reliance dynamic models have on executions. Our intuition is symbolic program representations can be deemed as a generalization of concrete executions. Directly exposing them as inputs should help to reduce the amount of execution needed to train a good model. Given our insights, the methodology easily follows. Let's start with the data format. We have given a formal definition of blended trace in the paper. Here I will just use some examples to illustrate. Given a program on the left, we perform symbolic execution to obtain a number of program paths. Let's take a simple path on the right as example, which execute statement 1, 2, and 3. Suppose we solve its path conditions and obtain the test inputs A, which has the value of I PLD, and B, which is PLDI. Then we execute the program with this input and record the state created at each step of the execution. Take the second step, for example. After statement 2 is executed, the variable tail has the value of PLD, wrap has the value of I, and RTN, which stands for the return value, is tau, i.e. uninitialized. Similarly, we can solve the path constraint to get another input, which will produce the 3 program states on the right. Given the concrete traces on the side and the symbolic trace in the middle, we group each statement in the path together with the states it creates in different executions to produce a blended trace. We name each step in a blended trace a tuple. With a different program path that can be triggered by other test inputs, we can create another blended trace. Now the question is, how do we learn from this data? To this end, we propose to embed a program at 3 levels: tuple level, trace level, and program level. First, I'll explain how to encode a tuple in a blended trace, and I will use the one highlighted in the shadow box as an example. Given a statement in a tuple, we extract its AST and fit into a tree LSTM, which produces the embedding HS along the static feature dimension. As for the program state, we treat it as the sequence of values and run them through an RNN. Specifically, we feed the value of each variable one by one to an RNN and take the final hidden state of the RNN HD1 as the first embedding along the dynamic feature dimension. Similarly, we take another program state in a different execution to produce HD2 as the second dynamic embedding. Suppose HP is the embedding of the previous tuple. We employ the attention mechanism to compare HS, HD1, and HD2 separately against HP to produce attention weight alpha, beta, and theta. Finally, we take the weighted sum of HS, HD1, and HD2 to produce HC, the embedding of the current tuple in the blended trace. Given the embedding of each tuple in a blended trace, H1, H2, Hn, that are already learned, we run them through another RNN and take its final hidden state as the embedding of the entire blended trace. Similarly, we can get the embedding of another blended trace, and eventually all of them. Finally, we perform a pooling operation to aggregate all the trace embeddings into a single program embedding. Although we strongly believe our approach is general, we incorporate more components into the network architecture to suit a specific downstream task, which is method name prediction. In particular, we use another RNN initialized with the H program and fed with the start token to generate a sequence of words. Like before, we use attention to fuse the hidden state of the RNN with the embedding of each tuple to generate a word. A word that is generated in the previous step will be used as the input as the next step. The process stops until the end token is generated. As one might notice, this is a typical encoder-decoder architecture, and all we did is add a decoder. We have realized our approach in a new model called Liger and extensively evaluated. We use Java Medium and Java Large true public dataset proposed by the prior works. We use Rendup, a test generator, to trigger executions. Due to the engineering issues we encountered, we can only get executions for a subset of the programs in both datasets. For baselines, we use code2vec, code2sic, which is the state-of-the-art model in method name prediction, and Dipro, a slight upgrade of the state trace model proposed in our ICR paper. We also reuse the metrics in prior work, precision, recall, and F1. Here's the results. Clearly, both models that use dynamic program features are more accurate than the static models. Especially Liger is the most accurate model across all metrics by a reasonable margin. Next, we investigate how Liger's accuracy varies with the amount of data. In this setting, we compare Liger with Dipro. We get the all program in the test set of the subset of both Java Medium and Java Large, on which we can obtain 20 symbolic traces and 5 concrete traces per symbolic trace. Then we gradually decrease the number of concrete traces per symbolic trace. Later, we start throwing out symbolic traces together with the respective concrete traces. Note that we keep the line coverage of the program when we dump the traces. Results show when there are sufficient traces, such as 20 symbolic with 5 or 4 concrete traces, Dipro is not far behind. However, when more traces are being thrown out, Liger shows a significant advantage. The experiment validates our hypothesis. That is, by incorporating symbolic program features into a pure dynamic approach, model becomes much less data dependent. We also performed an ablation study to review the contribution of each feature dimension. In the first experiment, we removed the trail STM for encoding the AST of each statement in the trace, and retrained the ablated version using the training set of the subset of the Java Large. For testing, we keep the same setup as shown in the previous slide, which starts with 20 symbolic traces and 5 concrete traces each. As we decrease the number to 4, the drop in accuracy is minor, indicating symbolic features are not so necessary when there are still enough concrete traces. But when we drop it to 3, we already see a notable performance gap between the ablated and the original Liger, suggesting that symbolic features become more important when less concrete traces are available. After throwing out more symbolic traces together with the respective concrete traces, we find Liger becomes significantly less accurate without the static feature dimension. The experiment demonstrates it's the symbolic program features that are responsible for Liger's resilience against the decreasing amount of executions. Then we remove the dynamic features and retrain Liger again. On the same test set as the previous experiment, Liger becomes a much less accurate model across the board, signaling the importance of dynamic program features on the precision of embeddings. Finally, we get rid of the attention mechanism and assign every feature embedding an equal weight. As we can see from the chart, removing attention also affected Liger's performance. Since Liger loses the capability to adjust the weight of each feature dimension on the fly, it decreases Liger's capacity of learning precise semantic embeddings. To conclude, in this work, we propose a new blended approach of learning semantic programming embeddings. In a method named prediction task, we show our approach is more precise than static models and less data dependent than a dynamic model. For future work, we plan to apply Liger to other problem domains to further test its usability and generality. That concludes my talk. Thanks very much for your attention, and I'm happy to answer any questions you may have.